Welcome, everyone. My name is Greg Risterman from Olympus NDT. I'd like to welcome everyone to this webinar on the OmniScan MX2 for improved TOFD. Our presenter today is Chris Magruder. Chris is the Phased Array AUT Manager for Olympus, has been developing and delivering phased array systems for over 12 years. This webinar is budgeted for about an hour. The main presentation should last approximately 45 or 50 minutes, leaving 10 or 15 minutes for questions. If you have questions, please type them into the Q&A panel in the lower right portion of your screen during the course of the presentation. Do not type your questions into the chat panel, as we do not monitor chat for Q&A purposes. If we don't get to your questions during the webinar, they will be addressed personally either by email or by phone after the event is over. Now, without further ado, I'd like to turn the presentation over to Chris Magruder. Chris, take it away.
Good morning, everybody, or afternoon or evening. I see we have attendees from all the continents today. We are very happy to present some new exciting TOFD equipment, software, and application notes for you today. The download that will come with this webinar will include the unabridged versions of all of these PowerPoints, the sample data files that we're going to be using, and the product brochures for the new instrumentation and mechanics. So we're here today to talk about TOFD, and particularly the improved TOFD capable in the MX2 OmniScan. And before we get too far into it, we want to give a slight overview for some of the attendees that might not have had TOFD experience or any formal TOFD training, a little bit about the application in theory, and then we're going to see it in several different environments, including the instrument and the analysis software. So getting right to it, TOFD, time of flight diffraction inspection, is a conventional UT technique that's been used for a long time. It's very simple in theory and setup, and it can be learned quickly. Within a couple days, you can know about 90% of everything you need to acquire TOFD data, and you can spend the rest of your career learning the rest of it. The TOFD analysis is weighted very heavily on the probe choice, the inspection strategy, and use of multiple TOFD groups. The actual acquisition of the data, again, is very simple. So we would generally divide the groups of TOFD students into two groups. Those that can acquire data in a procedure for which all parameters have been predetermined, and then a little bit more of an expertise, we would say somebody that's designing their own inspection strategies, probe selection, improving on a certain weld bevel, and the various parameters that make up that inspection. The new PA2 modules that have just recently been released from Olympus have allow an independent high-definition UT board for conventional UT that can operate simultaneous with the phased array groups. Where previous versions of this module only allowed an acquisition either from the phased array or the conventional B and C connectors from the first generation modules, now these two technologies can run simultaneously. And again, a high voltage independent high definition board optimized for TOFD or conventional UT. In this, we see the 32-128 phased array and UT version, and then a much more economical 2 TOFD group or 4 LEMO connector UT version of the same instrument. So these have a higher signal-to-noise ratio from improved electronics. B-scan imaging has been enhanced, and as much to do with our previous history of some TOFD complaints had to do with the PRF management that has now been improved in the software. So the new chip technology also has a lower power consumption, eliminating the need for the cooling fan on the 32-128s. That translates to longer battery life, ability to operate in hot environments for a continuous inspection usage between -10 and +45 degrees Celsius without triggering the safe shutdown of an overheat condition inside the electronics. Additionally, the new PA connector and ports allow an IP66 rating for the entire system to include the base unit and the module together. In addition to the improved module technology, we also have improvements in the probes and wedges themselves. The TOFD probes are designed to be highly dampened, broadband for low-level longitudinal waves in steel. Most common frequencies are 10 to 15 megahertz, and lower frequencies are used for thick components. They typically have a very small diameter of 3 to 6 millimeters for the most common TOFD groups, and then for thicker components, we use larger probes as well. New stainless steel wedges eliminate the need to use mechanical carbide feet. They have a lower profile and allow close access to the weld. They're available in the standard scanner holders or SLAs, and also new TOFD wedges compatible with the Cobra scanning for thin material, small diameter tubing. In the download, you will also see the probe catalog that contains the TOFD probes and wedges you see listed here. So the overwhelming majority of our TOFD inspections are a single group TOFD, typically combined with phased array, but using thicker components, expanding the TOFD to ASME vessels, thick components like this calibration block you see here, we would use small diameter, high angle, high frequency probes for the cap area, which is the most difficult to cover. And as the zones progress deeper into the material, they become larger in size, and they use lower frequency and larger diameter probes. And this is done completely through experimentation on the cal block for what works best, but it's fairly predictable. Our TOFD beam focus strategy, and again, the TOFD group is simply two identical conventional probes optimized for TOFD in a transmit-receive configuration. We would typically focus a single TOFD group at about 2/3 the thickness. That would give us good coverage on the top, ability to detect a notch, and good coverage on the bottom as well, with the weak spot being directly in the center between the probes. It doesn't matter which probe is used to transmit or receive. You'll receive the exact same results. So there's two ways to change the focus, whether we're doing that with a multiple zone technique or changing the focus to optimize on a particular weld bevel side or a thickness. And that is, you can change the angle of the wedge, and in this case we're looking at a 60-degree beam. 60 and 70 are very common angles for TOFD below 1 inch. Or you can change the PCS. By moving these probes in and out, it will essentially move this focus point up or down. And we'll see the theoretical coverage from the beam simulation in the beam plotters. There's a very simple calculation that's used to arrive at the PCS. And again, PCS is probe center spacing from exit point to exit point, not probe base to probe base. This is calculated automatically in the beam plotters like the NDT Setup Builder from Olympus or the ES Beam tool from Eclipse, or it can be done very easily on a calculator. The PCS configuration, when using the NDT Setup Builder or similar beam plotter, again, instead of entering the calculation, we simply select the probe. The software knows the size and frequency, we know the model and the wedge, and then we simply just type in the focus distance or percent of thickness we would like, and it will automatically adjust the PCS for us. TOFD uses an unrectified RF waveform, or A-scan. This A-scan is available from almost every conventional UT flaw detector with pitch catch capability, or two BNC or LEMO connectors. It's very simple in its application. What makes a TOFD system unique or more complicated or more expensive or require the need of a computer is not the A-scan generation, but rather the B-scan generation. It's the B-scan imaging, encoder capability, calibration, and sizing tools found in dedicated AUT systems that make TOFD possible. But the actual electronics to generate the A-scan waveform is typical of any conventional or digital flaw detector. So we'll talk a little bit about the A-scan basics. The area of interest for the TOFD inspection is between the lateral wave and the back wall, and we'll see some graphics of this that explains this a couple of different ways. Between the lateral wave, here represents the surface of the part. Here in the A-scan, here in the B-scan. The back wall is the next signal, and this is a longitudinal velocity between the surface of the component and the back wall, and it's strictly a time of flight inspection. Amplitude is not so significant. Then between the back wall here and the shear wave mode converted signal, the sound is traveling at a different velocity. So this area has value for identifying defects, but our area where we're going to measure, calibrate, is going to be between the lateral wave and the back wall you see here. So TOFD inspection is based on a diffraction signal not dependent on flaw orientation. That makes it very advantageous for weld inspection. Incoming waves vibrate in every direction and radiate energy. The sound energy is very low level compared to reflected energy, and the diffracted energy travels at a fixed longitudinal velocity that can be calibrated. Mode converted shear wave is also present in the data, and again, sharp defects, lack of fusion, cracks, linear type indications create the best emitters. So the A-scan basics require a transmitter probe and a receiver probe in a pitch catch configuration. The signal traveling on the surface or directly between the two exit points is called the lateral wave. And notice it has a positive, negative, positive phase. The next signal that arrives on our A-scan in a weld with no flaws would be the back wall. And again, notice the phase inversion is out of phase with the lateral wave of negative, positive, negative. Any flaw that shows up between the lateral wave and the back wall can be measured very accurately for depth, height, and length. So the tip diffracted signal, and again, out of phase with the lateral wave, and the bottom tip out of phase with the upper tip, tells us that this is a continuous flaw. When a surface breaking flaw is inspected by the TOFD, the lateral wave is obstructed and not present. So the first signal we'll see is the crack tip here. Anytime we lose the lateral wave signal while maintaining the back wall or some other signals in between it is an indication of a surface breaking flaw, typically of a crack, and it's indicated by no lateral wave. It's exactly the opposite for a surface breaking flaw on the opposite, or the ID. The lateral wave is present. The next signal we see in the data is the upper tip. and we will either see a distorted back wall or no back wall, depending on the severity of the flaw. In a interpass non-fusion, which is very common in weld inspection, but not typically detected by the RT or pulse echo, we'll see the lateral wave, the back wall, a small indication for the flaw echo, but no measurable significant depth and height. This accounts for a lot of the irrelevant or noise that you see inside of a TOFD group that cannot be proved up with pulse echo, UT, or radiography. One of the limitations of TOFD is that it cannot differentiate which side of the weld or where on the index axis a flaw is. Any flaw occurring at a position 1, 2, or 3 would have a similar appearance in the TOFD data. So I can know its length, depth, height, to some extent characterize the flaw, but when making a repair on a thick component, I wouldn't be able to tell where in relationship to the probe face I would need to excavate. So for this reason, it's often combined with manual prove-up or pulse echo or phased array probes during the inspection as well. So the TOFD B-scan imaging, or the TOFD software that we need to make TOFD useful, uses an unrectified A-scan and converts time and amplitude to a black and white image. Black is negative in the grayscale, white is positive, and then it's scaled in intensity based on amplitude. Every 1 millimeter of travel of the scanner generates one line in the B-scan that is a representation of the A-scan waveform. So the B-scan imaging, we will typically see the scan axis represented by the blue line or the blue ruler represents the movement of the scanner. Every 1 millimeter or whatever the inspection resolution is entered, the software will acquire a new piece of data or A-scan. This axis is the UT axis. It represents the A-scan time base, and we will set our range so that we are covering the lateral wave and approximately 1 microsecond before the lateral wave, and we will either include the back wall or not, depending on the need and the procedure and the preference. In this case, the back wall is not being, or the mode converted shear wave is not being displayed, but the back wall is. The back wall is. Prior to calibration, while we're working in inspection mode, when we're setting it up, the UT axis here is in microseconds or time. It won't be converted to millimeters in distance until it's calibrated and converted in the software, which is typically done in analysis mode where sizing and recording of defects is necessary. The B-scan imaging is also skewed in that it doesn't represent the weld in a linear manner. In other words, in a typical B-scan, you see here, the first half of the weld, representing 0 to 6 millimeters in this case, is actually approximately the first quarter of the B-scan. Okay, the next half of the weld, or the 7 to 12 millimeters in this case, is represented here, and you can see it's much larger. This has to do with the time base between the back wall and the lateral wave, and it makes flaws near the surface much more difficult to detect, characterize, and size than flaws in the lower half of the weld. Use of high frequency, very small probes is important for this reason. The B-scan imaging, like I had said, may or may not include the shear wave mode converted signal you see here. Here we have the lateral wave, and we see a defect detected both in the L wave and the mode converted shear wave. So our ability to measure in this area is limited or non-existent, but it's useful in identifying defects. Here we see a change in thickness during the inspection, and the range was set on the UT to include the full mode converted shear wave. The mechanical requirements for TOFD are also very simple. It's for a one-line encoded scanners pushed by hand or full mechanized multi-probe UT, the scanner must hold the probes steady and stable in relationship to the weld and be able to roll smoothly. Scanners come in all shapes and sizes that can accommodate different probes and wedges or multi-group or single group. Here we'll have magnetic wheels, adjustable bar. The probe holders, PCS, are adjusted, and we have an encoder here either leading or trailing the phased array probe or the TOFD probes. Included in the download for this webinar is a new single scanner Olympus is marketing and including in their packages that has a lot of up-to-date useful features. A very hardy, durable, easy to manipulate, one-hand control. It's got a very nice encoder that doesn't slip when it's wet and in the couplant, easy adjustable magnetic wheels, and very, very useful. The new wedges that you see, the stainless steel wedges, will allow us closer access to the welds for near surface coverage, eliminates the need for mechanical feet, and provide a better, more stable platform for the TOFD data, and less of the hassles that come about from the lateral wave distortion from the mechanical feet that are required for Rexolite wedges. And again, a simple water supply here, and these probes are marked for the exit point, so it can easily be seen for measuring the PCS. Obviously, an automated scanner with a laser system that can be guided slightly by the hand, but it doesn't require your energy to push it, is going to acquire data at a much better and more efficiently and faster and smoother than a manual push scanner. But the overwhelming majority of TOFD that we see done now is being done by the semi-encoded or encoded manual push scanners. The majority of Olympus sales for TOFD are also combined with phased array. The new version 4.0 of the OmniScan software that's available for Omni PC and on the instrument now has the default views rearranged to not include the A scans. A typical two-sector scan, one TOFD channel coverage in any number of different scanners can easily be generated in the beam plotter and planned, then imported into the instrument. The acquisition is done with a set of TOFD probes and phased array probes on the same scanner at the same time, and it's the core application that accounts for the overwhelming of our TOFD and phased array sales. Up to about 30 to 40 millimeters, depending on the code and the procedure and the customer preference, is where we would break an inspection up into multiple zones. The amount of zones that you use, and again here we're showing one TOFD zone with overlapping phased array coverage, would be dependent on your expected sizing required. TOFD is extremely useful for weld bevels that cannot be inspected at a perpendicular angle to the weld bevel. A 30-degree weld bevel can be inspected with a 60-degree angle very efficiently. But with the weld bevel is either narrow, like in most pipeline and vessel automated, semi-automated welding processes, it becomes a very low probability of detection on a vertical or near vertical plane. Weld bevels of 10 or 15 degrees are not uncommon, and where we cannot use a pitch catch probe like done in the pipelines, the TOFD increases the probability of detection on this weld bevel enormously, and that's why it's useful. Why use TOFD if you're using phased array? Improved length sizing, depth and height sizing, and improved detection of flaws that are not perpendicular to the weld bevel or to the beam of the probe. There are also different advanced TOFD strategies. These, with the exception of this one, these two scanners are customized modifications that are not core products from Olympus, but just examples of what some customers are doing, whereas we can introduce the TOFD at an angle for off-axis inspection of the weld line, and then the scanner can be rotated to take it in the other direction, and that's a customer requirement by some of the end users or buyers of phased array services around the world. Another technique would be to build a sled for a weld all in one housing, where we've integrated the TOFD group with pulse echo or pitch catch weld inspection zones. This would be maybe good for a high production, high volume facility that uses a finite number of weld bevels, such as a windmill tower or some other type of constructor. There's positives and negatives with this type of setup. The benefit is it's extremely easy to set it up and get it running, but your ability to manipulate the probes and to couple well and provide total couplant across all of those requires a much more water and a smooth, smooth pipe surface or tower surface. And then a standard scanner like the X03 below is unique in the scanner catalog in that the wheels rotate 90 degrees, so I could scan either parallel or perpendicular to the weld line. And again, the actual TOFD mechanics are fairly simple. They come in all different shapes and sizes. They would include wheels, an encoder, a series of TOFD probe holders for 1, 2, 3, 4 or more TOFD channels. They may or may not include remote pulsar receivers, built-in water supplies, umbilicals with all of the cabling. They may or may not include phased array probes along with the scanner as well. Again, in the Olympus catalog and available from a number of manufacturers, we'll see many different versions of this. In this example of an advanced TOFD strategy using TomoView for analysis, we'll see that an SAW weld station has been converted to a phased array TOFD station using multiple zones for thicker components. The TomoView release, compatible for analysis of the new modules, PA2s, will be released in March. This is upcoming. Previous generation modules can be converted now using a TomoView display like you see here, where both the TOFD displays, phased array zones, sector scans, and phased array merged C scans can be customized and rearranged as necessary. Improved TOFD for the MX2 also includes probes, wedges, and mechanics for what were traditionally too thin of components or too small of diameters to inspect. We're having success now with higher frequency, small diameter, thin wall components, and in this case, we see an 80-degree TOFD L-wave inspecting a 1.75-inch diameter, 4.6 millimeter thick component. And one other point, when using the TOFD probes or L-wave phased array probes with the Cobra scanner system that's a much larger standoff or a much larger spacings required than the 12 millimeter that's capable with the small phased array version of that inspection. So we talked a little bit about the overall setup and some basic theory, and we've seen some images now of some scanners and B-scans and scans. Now we're going to go through the process of setting this up on the MX2 instrument, which will include connectivity through the NDT setup builder, which is a beam plotter from Olympus that we use for phased array and TOFD. It will take us through the setup of the group wizard on the MX2. We're going to configure the UT, configure the scanner, talk a little bit about the mechanical setup, and do a simple demonstration of acquisition, analysis, and reporting. The inspection is possible either with a one TOFD group and or phased array TOFD combination depending on the available mechanics, scanners, and probes. And we'll talk a little bit about a multi-group as well. So the SUB NDT Setup Builder software is our beam plotter that has direct connectivity into the MX2. With one group, it's probably not faster to do that on a computer and import it, but once we start doing multiple group inspections, it becomes much faster and easier. So we're going to transition away from the PowerPoint for a moment and take a look at the NDT Setup Builder that you see here. It's a very simple user interface. We select our acquisition unit that will tell us how many phased array pulsars, multiplexed channels, and UT channels are available. So that will limit us in not creating something not compatible with the instrument that we're using. They come in all different configurations. Then from the probe tab, we simply add a probe. We change it to a TOFD. And all of the probes and wedges from the Olympus catalog are in the database. We select the probe and the appropriate wedge, the orientation to the weld line. The PCS is manipulated automatically based on the beam that we'll see shortly, and the pulsar connection and receiver connection. For our groups, the TOFD group is automatically generated. We can select the color, and we chose to focus this at 66.7, or about 2/3 of the thickness of the component. The component is built directly in the software. It has a simple user interface where you enter the dimensions of the plate, you form the weld bevel, enter the various sections of the weld bevel, and can create most symmetrical and asymmetrical configurations. Again, in a one group configuration like we see here, it's not beneficial to import into the software. It's faster to do on the instrument. But where we see a multiple configuration setup, like we do here, where we're using 4 independent TOFD groups to inspect a 100 millimeter vessel, we would start out with a cap group using small, high frequency, and it would become larger and lower frequency towards the bottom zones. In this instance, we can export directly to a connectivity file that will import into the OmniScan to allow us to be able to have all of those zones and pulsar connections and beams and PCS and all the parameters automatically entered into the instrument. So the SUB connectivity combining the phased array and the TOFD is what we use to do the overall basic inspection strategy. Then we're going to physically connect the probes to the instrumentation. Prior to setting up the UT, you must adjust the probe exit points to the PCS that was calculated either in the software or by the operator. The connections of the coaxial cables are made directly into the LEMO connectors or to an adapter here. Again, this runs simultaneously with the phased array now. Because of the high voltage that's available on the UT channel, and we'll have a voltage available on the new modules that you see pictured here of 95 low, 175 volts medium, or 340 volts high, which eliminates the need for remote pulsar receivers on this connector. On multi-zone techniques where we're using pins from the phased array combined with this, these may or may not be necessary. But any weld now under about 30 or 40 millimeters would not require additional remote pulsars and receivers. The signal-to-noise ratio is dramatically improved over previous versions. So in the software, the wizards are going to take us through every little step of the setup. It's a simple wizard where we configure the probe and the part and the weld first. And in the setup of the TOFD group, it takes us through step by step all of the relative sections for the instrumentation, probe, wedge, scanner, and basic scanning parameters. Our scanning sensitivity or details will be regulated typically by the codes. In the ASME Section 5 code, it specifically tells us how to set the scanning sensitivity. It has a lot of latitude for the user to develop their own technique for what works best in one situation. And we are going to take a minute and transition again away from the PowerPoint to take a look at the instrument live. So we're looking at the MX2 in normal mode directly on the presentation. The A scan we see now is live. So we're going to set up our TOFD group by starting with the wizard. Everything starts with the wizard. Our part and weld was previously configured as a 12.7 millimeter thick carbon steel plate weld. Our setup wizard is going to take us through all of the various steps. So we can either add or modify or delete any group. This TOFD group would typically be group 3 behind 2 phased array groups. Or it could be a multiple group inspection strictly of TOFD. So in this case, we're going to add the group. We will take a default parameters, and we'll see now with the new generation of instrumentation and software, we have 3 options. The options that you see are either for the UT conventional, directly in a LEMO connector on a compatible module, UT conventional using an adapter through the phased array connector, and in this case, we would be borrowing 1 or 2 of the 128 available pins from the phased array connector. So this would typically be 63, 64, 127, 128, or a pure phased array group. So we're going to select conventional UT using the conventional UT connector and select next. Okay, change the mode to time of flight. and we have selected the P1R1 by default, so the pulsar knows the instrument's LEMO connections. It's an L-wave inspection. Select next, 10 megahertz. We will enter the angle of the probe just for recording purposes. It's not relevant to the calibration. Setting the frequency of the probe will automatically set the correct pulse width. We can enter any scan offsets and the calculated PCS for our group. Our scan offset would be necessary for when we have a multiple probe configuration. 0 would be the phased array probes, and then the TOFD would typically be trailing by some number that would be entered into the scan offset for that group. Select next, and we can finish. So we have our UT group, our TOFD group now set up and visible. We want to set our range on the UT setup so that we can see approximately a microsecond in front of the lateral wave, and maybe the mode converted shear wave and some distance in back of that, depending on the procedure and the preference. Our pulsar, the frequency was automatically selected during the wizard process. We will use one of the 3 available voltages for what works best, paying attention to the signal to noise ratio. The pulse width was automatically set. The PRF, which is managed blind to the user or can be controlled manually, optimizes now the TOFD group inside of a multi-group inspection with phased array. Probably 1/2 of the culpability for the OmniScan's reputation for weak TOFD was due to PRF management generating excessive noise when combined with use of averaging. That has been corrected, and we see an enormous improvement now in both signal-to-noise ratio and detectability in B-scan imaging as a result of software in addition to hardware. So we select the receiver, select the filter of the frequency or whichever filter produces the best results, including no filter if the results are better. Experiment with the averaging. More than necessary isn't really going to help you, but will slow down the acquisition, so use what works best. When we're setting our initial inspection sensitivity, typically we want this lateral wave set somewhere between 40 and 80%, depending on the code. We want to pay attention that the back wall is not saturated or has excessive ring down cycling, and we want to make sure that our range is good. Calibration is taken care of normally in inspection or in analysis mode. So all we need to acquire the data is to ensure that enough gain for good sensitivity and that the range has been selected properly. Under our displays, we're going to configure a specific group for TOFD. These are our 2 groups of 8 readings at the top of the instrument. And our normal display for the TOFD will include an A scan and B scan that you see here. We will set up the scanner. Going to the scan menu, we're going to change the default from time to encoder 1. This is telling the software that we are now going to fix the pulsar at the speed of the encoder. When I move the scanner, this B scan will start to build, and I must enter in the parameters of the encoder, which can either be entered if you know them or calibrated using the encoder calibration wizard. The area of the plate and the inspection resolution. In this instance, we're going to acquire 1 A scan every 1 millimeter, which is typical of most of our inspections. Smaller diameter piping, better length sizing requires a higher scan resolution, and this is directly related to scan speed and file size. We will enter a file name, for the data file that we're getting ready to acquire, and we're going to acquire all A scans. So at this point, the instrument is ready to start acquiring data. I'm going to take a small acquisition here on the plate. So we're going to wet down the plate well. I'm going to position the scanner in place on the component. I'm going to select the start button on the instrument and hit yes. This will zero the encoder and prepare the instrument to take an acquisition. I'm going to move the scanner slowly and smoothly, acquiring the data. The data is acquired in two directions, so I can back up. Or continue scanning to acquire the data. Any data line that's missed shows up as a black line, and then we can back up and reacquire it. So after the data is collected, I select pause on the instrument, and I'm ready to save the data file. Now we transition away from the instrument back to the PowerPoint and talk a little bit about calibration before we get into analysis. So calibration is simple in its application, but fairly complicated in the strategy and the math. If you know 2 or 3 of any of the parameters, such as velocity, wedge delay, PCS, the position of the lateral wave and back wall, you can arrive at the calibration you desire, which ultimately is converting the A scan from microseconds to millimeters. We're going to use lateral wave straightening prior to calibration so that the data is aligned and easier to analyze. As the scanner is acquiring data, the start position of every A scan is distorted slightly, and that can be straightened in the software. The area of interest is our longitudinal area between the lateral wave and back wall. This is our area that can be calibrated based on a fixed velocity. We're going to identify our cursor position of the lateral wave and back wall in accordance with our procedure. There's not unanimous consensus on that, but the overwhelming majority of users are using the first peak and then the opposite first peak on the back wall. Full explanations of these are available in the downloads. We will convert this area of the A scan from microseconds to millimeters. 0 representing the lateral wave, and in this case 12.7 millimeters representing the back wall. And then that takes care of the A scan and the B scan for our ability to size and record defects. The offline viewer or analysis software we're going to be using is OmniPC. OmniPC allows the same user interface as the OmniScan MX2 offline on a computer. So we have the raw data that we see here in our TOFD group. We go straight to the wizard, select calibration, lateral wave synchro, start. Okay, the software asks us for a representative A scan with no defects. We're going to place a cursor to identify the lateral wave on the A scan and the B scan on both sides. So within this area, the software is going to take the first peak and straighten the entire scan and align all of the A scans on the B scan. So now it has been straightened here. It makes the analysis easier and it makes the sizing more consistent. Select Accept. Now we will calibrate wedge delay and PCS. Again, this is a new feature for the new 4.0 version of the software to include the PCS calibration. Take a representative A scan, enter the thickness that has defaulted from the component. We will identify the lateral wave, first negative peak, the back wall, first positive peak, and this will convert microseconds to millimeters. 0 representing the part surface, 12 millimeters representing the part back wall. Select Calibrate, and we can see the velocity looks normal, the wedge delay is good, and the PCS has been entered. We'll select Accept, and now we'll see that 0 millimeters and 12 millimeters are linear inside our area of interest. So we will zoom in on a portion of this, and the hyperbaric cursors are now available that aid us in length sizing. We'll place a cursor along the hyperbolic position of the flaw. We see that this is an ID connected crack. I'll identify the left and the right side of it. Put one cursor at the back wall. And under our measurements, readings, we will use the TOFD so that our flaw starts at 5.78 millimeters in depth. It has a through wall dimension of 6.24 millimeters connected to the ID, and the length starts at 41 for an overall length of 21 millimeters. So I've positioned my cursors. We can do this full screen, and we can directly add the indication to the indication table from here. We also have the ability to look at that same component with the phased array. So we'll see here the TOFD crack that we just analyzed. We can see the TOFD crack in the phased array groups as well. The report that we just created based on the TOFD group can be seen under File, Report, Preview. That includes all of the setup information and the TOFD with the statistical information that can be printed directly from the instrument or saved on the flashcard. Again, the calibration typically done in analysis mode after the inspection when flaws are needed to size. So I saw we had quite a few questions during the presentation. The MX2 can display up to 4 groups of TOFD and 4 groups of phased array simultaneously using software version V4 or later. That's a very important point. And on the full versions of these training PowerPoints that you'll see in the download, there's some more images and some more examples of that. Good question. There was several other questions that we didn't have time to get to. We will answer all of those for you in the email blast that follows this up. So we've used up our time for this webinar, and this was MX2 Improved TOFD using the OmniScan MX2. I'm going to turn this back over to our moderator, Greg, and I want to thank everybody for attending and hope to see you guys again at our next application webinar in about a month. We'll see you then. Thank you very much for attending. Greg.
Thanks, Chris. Nice job. On behalf of Olympus, I'd like to thank all the attendees for joining us today. I'd like to thank Chris for his participation. We hope this material was informative and useful to you. This webinar, along with the Q&A, will be archived on our website at www.olympus-ims.com. Follow-up emails will also go out to all registrants for this webinar with a link to download the files used in this presentation, as well as a link to the archived presentation. That's going to do it for today, and again, thanks to everyone for participating, and we will see you again next time.